We're going to do section 5.1. This is part 2. In this section, we're going to focus on Euler's method. Euler's method is a numerical method to solve differential equations. We're going to go ahead and review our analytical method, which is separation of variables. At this point in the book, they actually haven't introduced this yet, but we did learn it last year, so I'm just going to take this opportunity to use it as a setup for the need for this. Okay, so let's say we have this differential equation, and we want to solve the particular solution for 0, 5. Okay, so first of all, we're going to separate the variables. Y dy is equal to x dx. Integrate both sides. 1/2 y squared is equal to 1/2 x squared plus c. Keep in mind we only need the arbitrary constant on one side, but we definitely need that arbitrary constant. If you leave it out here, your information is going to be way, way off. So now I'm going to multiply both sides by 2. Y squared is equal to x squared plus 2c. There's no point in calling it 2c. It's an arbitrary constant, so we'll just leave that c. All right. Now we're going to take the square root of both sides. Don't forget the plus or minus. So y is equal to plus or minus square root of x squared plus c. Now that's a general solution. Having the plus or minus in the general solution is fine, but understand once we plug in a point, the plus or minus is going to make this so it's not a function. We're interested in a solution that is a function. So we're going to accept the positive or negative based on this point. So since I'm plugging in 0, 5 here, my y is 5, which means we're going to accept the positive of this, not the negative. And now we're going to solve for c, which is quite easy. 0 squared plus c is c. Take the square root of that. We're going to square both sides, so we get 25 is equal to c, and then we plug it in. Okay, so this is our analytical solution equation, and it's pretty easy stuff. So let's say we wanted to find what our value is for f. So we could say y is equal to f of x for, let's say, 2. Well, that wouldn't be an issue. All we would do is plug 2 into this, and we would get 4 plus 25. So that would end up giving us square root of 29. You can leave it like that. If you do change it to a decimal, I want to remind you that we want to make sure we're accurate to 3 decimal places. So we would get approximately 5.385 and then 1. So you can either truncate around that to 3 decimal places, or you can do as I did and leave it to 4 decimal places. So what we're going to do is, next we're going to look at an equation where we can't do that separation of variables, but we still want to be able to come up with at least an approximation for a solution here. Okay, so this was the exact square root of 29. Let's see if we can't separate the variables. All right, so here we have another differential equation. Dy over dx is equal to x plus y. We have the initial condition f of 0 is equal to, so the point 0, 2. We want to find an approximation for f of 1. Okay, here's the problem. We can't find the exact here because we cannot separate these variables. When we do separation of variables, we can only move things across the equals by multiplying or dividing a whole quantity here. So you can't like subtract the y, you're going to get stuff that doesn't really make sense. So we have no way of finding the exact solution curve analytically. Okay, so one thing we did in the past was we did a tangent line. So let's say we were doing this particular problem, and let's say we did a tangent line here. So I have the point 0, 2. So if I was going to do a tangent line, I could get the slope of that tangent line by just plugging in dy over dx. I can plug 0 or 2 in the dy over dx, which is going to give me 2. So now I have a tangent line, so we can just do this in slope-intercept form, of y equals 2x plus 2. So I can approximate f of 1, and this is something we did do last year, by plugging 1 into that, which would give us 4. Okay. Now we don't really know how good of approximation is. We would have to assume it's not necessarily very good. We're going quite a long distance. Here to get that value. So we're going to 1, so we're getting So we have some curve here, whatever that looks like, we don't necessarily know. We could do slope fields to kind of get a feel for it, but we have a tangent line here. Okay, you know, it doesn't look like a curve. It's not necessarily a good approximation. So what we're going to do instead here is, and then we'll get to Euler's method. This is technically Euler's method, but it's just one equation. Euler's method is about using not just one tangent line, but using a series of tangent lines. So let's say we said we wanted a better approximation. So what we're going to do instead is we're going to say, hey, well, what if we did this slope right, or this equation right here, but we're not going to use it to get all the way over to 1. We're going to use it to get at 1/2. So we're going to call this L sub 1, okay? So we're going to approximate f of 0.5 by using L sub 1 of 0.5 instead. And so that gives us 3. So now I have the point 0.53. Okay, so I'm using this right here. Now what I'm going to do is I'm going to write another tangent line using the new slope. Okay, so now I have a new point. My new point is 0.53. Okay, now we're going to write a tangent line from that particular point. So from 0.53, all right, I'm going to plug it back in here, dy over dx of 0.53, and that gives me a slope of 0.5 plus 3, so that's equal to 3.5. All right, so now 3.5 is my new slope. Now, I'm not going to use slope-intercept anymore. I'm going to use point slope, but I'm going to use that point slope where I'm not going to do y minus y1. I'm going to put the y1 on this side. Okay? So now, we're going to plug in this point. So this will be y equals 3 plus 3.5 is my slope. So we're just writing a tangent line from here based on this differential equation. And this is going to be x minus 0.5. Okay? So now we're going to use this right here, call this L sub 2. So this one was L sub 1. Now this is going to be L sub 2. So now we're going to approximate f of 1 using this L sub 2. So L sub 2 of, and then 1. So we're going to plug 1 into this. So that will give us 3 plus 3.5. And then plug 1 in, that's going to give us 0.5. So I'm going to grab the calculator here. By the way, when we do this in class, I'm going to show you some calculator tricks that will make this a little bit easier. So this will be 0.5. And this gives us 4.75. So now we have what we would have to assume is a better solution. So now we're writing another tangent line up here, okay? But still not necessarily a great approximation. So now we get to sort of a typical calculus idea. Well, what if I wanted a better approximation still? What could I do? I could use 4 tangent lines. I could use 8 tangent lines, et cetera, et cetera, et cetera. You can see with this that it's going to get quite complicated to keep doing this process. What Euler's method does is it just makes this more streamlined. You're doing the exact same math, but you're basically using this formula to make it a little bit easier. So let's do that. Let's do this exact same problem here. This time we're going to use 4 tangent lines, or what we call 4 steps, and we'll use Euler's method this time. Do 4 steps or 4 tangent lines. So I recorded what we got from the 1 tangent line. We got 4. From 2 tangent lines or 2 steps, we got 4.75. So now we're going to do 4. I'm also going to show you on your calculator how you can do this and save yourself some sanity, because we do have to have our final answer be accurate to 3 decimal places. So anyways, this is our point slope form. This is actually what Euler's formula is based off of. So what we end up doing is, when we do, if you think about the way these work, was we were always using the point prior to get to the new value. For instance, here we went from, use the point at 0 to get 0.5, and then 0.5, we use that to get 1. So it's really a recursive pattern. So to get y sub n, we're going to use the y sub n minus 1 of the point prior plus, and then you're using the point prior by plugging in a differential equation. I'm going to call that f prime, just because it's a little bit cleaner. Now, the x minus x1, since we're always using the point prior, that's always going to be equal to the increments that we're going by. So for instance, here it would have been 1, okay? This one would be 0.5. This one, it's going to be 0.25 because we're going with 4. This is what we refer to as the delta x, okay? So we're doing 4 steps, and since we're going from 0 to 1 with 4 steps, our delta x is 0.25. Okay, now, here's the deal. You can organize how you want. I like to use a table because it really helps. Okay, so I'm going to make a little table here. All right. So we're going to have x sub n. I like to put the preceding point here because otherwise you kind of can get confused between the two. Okay, and this is where we're going to get our y sub n. This is where we're doing the calculation. Okay, now these are the x sub n's. So our first x sub n, if we're starting at 0 and our delta x is 0.25, is going to be 0.25. Our next x sub n is going to be 0.5. Our next sub n will be 0.75, and our final x sub n will be 1, and that's where we're actually going to be getting our approximation. Okay? So now, the preceding point, we start with the first point, so that's going to be 0, 2. All right? Now, I'm going to write this out the first time, but it gets a little cumbersome after a while. All you have to do is make sure you're showing that you're using Euler's method, and you're going to be good here. So we start with the preceding y value. Okay, so that's going to be 2, plus, then we take the preceding point and plug it into our differential equation, 0 plus 2, okay? And then we're going to put our delta x, which is 0.25. All right, well, this one isn't a big deal, right? We don't really even need our calculator for this, because 2 times 0.25 is 0.5, so this will be 2.5. All right? Now, this point, this x goes here. Okay, so this is a recursive pattern. For those of you in computer science, you're familiar with this kind of thing. And then this value goes here, and that goes as we go along. So Euler's method just keeps us, this helps with sort of organizing this. Oops, decimal point's in the wrong spot. Okay, now, instead of doing this each time, what I'm going to do is I'm going to plug this in my calculator. So what I want you to do in your calculator is, if you initialize the 2.5, so first thing you're going to do is enter the 2.5 in your calculator. Hit enter, okay? Whatever that value is here. So you have to initialize that. Enter your calculator, hit enter. Now, so we can just keep bringing that back in. In your calculator, hit second answer. Okay, so this is what you're going to put in your calculator. Second answer, plus, so we're actually going to put Euler's formula in our calculator. Plus, okay, now we're going to use this differential equation. This is the only value we're going to have to change is this x value. So in this particular case, it's 0.25. To save yourself some room here, so you don't have to keep doing insert, call it 0.25 plus, and that's going to be that y value, so this will be answer. So if you do this, you don't have to keep track of all this work you're doing, and then finally, this will be 0.25, okay? So this is what I'm going to enter in my calculator after I initialize the 2.5. And we can talk about this more in class if this is confusing. So second answer, parentheses, 0.25 plus second answer, and our parentheses, and then I'm going to put 0.25. And then hit enter. So this gives us 3.1875. And the reason we want to do this is, we know we have to be accurate final answer to 4 decimal places. We're going to get a bunch of decimals here. I don't want to have to keep writing those out. If I do this, I can have this in my calculator. So now, let's start the process again. This is 0.5. This is going to be our 3.1875. Now, in our calculator, if you hit second entry, it's at the enter button, it will bring up what we already have. The only thing you need to change, because it will automatically take care of the 3.1875, because that's going to be the answer, is the 0.5. So let's change the 0.25 to 0.50. Now hit enter. So now we get 4.109375. So you can see the importance of learning this little calculator trick. It's going to save you a lot of time. And then we plug these points in, 0.75, and then it's going to be 4.1093. I'll leave it there. I'll let the calculator do the work. And once again, I'll go second enter, bring up that calculation, and the only thing I have to change is in here. I want to change that to 0.75. Hit enter, and I get 5.3242. I do that with 5.3242. Okay, and so that is my approximation, and we can see that the first one was way far away from that. And we could do this process, you could do this with 8. I typically keep it to 4 or 5. Your textbook you might do a little bit more, but you know, that's Euler's method, and it'll make this a little bit easier. I'll do one more example. Okay, so here's another example. I use slightly different notation. I also put a little hiccup here. So here's our differential equation expressed as f prime of x, that's equal to 2x, y. We're given f of 1 equals -1, so that's our initial condition. We want to approximate f of 0, and we're going to use 5 steps. The thing that's a little bit different about this one is realize that here we're starting at 1 and going back to 0. So we're actually moving to the left instead of the right. So if I move to the right, my delta x is going to be positive. If I move to the left, my delta x is going to be negative. So delta x is going to be negative, and so 5 steps, 1 to 0, that's going to be -0.2. Okay, so let's make our table. Once again, Euler's formula, let me write that down. Y sub n is equal to y sub n minus 1 plus f prime x sub n minus 1 comma y sub n minus 1 delta x. Okay. So let's see, x sub n minus 1 comma y sub n minus 1. This time I'm going to do this completely in my calculator. So the y sub n I'll do in the calculator, and I'll walk you through that trick again if you had a hard time following that. Okay, so let's plug in the initial point, which is 1, -1. Okay, so that means my first x sub n will be 0.2 to the left, so that's going to be 0.8, then 0.6, 0.4, 0.2, and we're interested in 0. How many rows you have here will be equal to the number of steps if we did this right. So 1, 2, 3, 4, 5 steps. So we're good to go. Okay. Now, once again, what I'm going to do in my calculator is I'm going to initialize that initial point. Okay, so I'm going to start off with whatever that value is, and I'm going to enter at my calculator. So right now, hit -1, enter. Now, once you have in your calculator, you can build this with your calculator. So once you initialize, -1 and enter. Now we'll use a different color here. So once we do the -1 enter, we're going to enter in our calculator answer plus, and then our differential equation, which will be 2x, which, let's see, let's call it 1.0. That way we don't have to hit the second insert. Y, we use answer, and then our delta x here will be -0.2. So let's enter that in our calculator. So So I hit enter, I get negative 0.6, okay? And then, once again, it's a recursive process, so we take the values from the row ahead, so 0.8, negative 0.6. Now, in my calculator, I go second entry, bring that back up. Now, all I have to change is this right here. So instead of 1, I'm going to change that to 0.8. Everything else will take care of itself. So that gives us negative 0.408. Now this is my new point. So Euler's method is pretty easy once you get it down. It's just about sort of understanding what's happening here. All right, and then once again, second enter, bring that back up, and we're going to change that x to 0.6. And we get negative 0.31. Let's call it 00, but there is an 8 at the end of that, but we have that in our calculator, so no problem. 0.4, bring that down, negative 0.3100. Second enter, bring that back up. We're going to change that to 0.4. Enter, we get negative 0.2604, and we're almost there. 5 is usually the most for me. I think in the book they have you do one that's a little bit longer. I think it can be a little bit overkill. Negative 0.2604, that comes down. Second enter. So all we have to do now is change the x to 0.2. Hit enter, and we get negative 0.2396. And that will be a perfectly fine approximation. So that is Euler's method.